Hi, I'm Alan Dix, and I want to talk to you today about the mathematics of intelligent fairy lights. So fairy lights are fun, and at Christmas time they're very pretty, sitting on the tree. But the ones I want to talk to you about are intelligent ones. Here's a picture of some of the lights I want to talk to you about, and we called them Firefly technology. They have a different name commercially when we licensed them, but Firefly was what we called them. Now, they don't look very special just as a set of lights like this, but I'll explain more about them later. The lights here are outside a building called InfoLab in Lancaster University, and that was where some years ago I worked with Joe Finney. And Joe Finney is the other person to think about here, but also lots of other people there worked at the same time on this. The reason I mentioned Joe Finney particularly is not that you will have heard of him, but it's almost certain you will have used or heard of, certainly, some of the software that he's produced, because Joe Finney is the guy behind all the software that runs on a microbit. So if you've ever programmed a microbit, or if you've heard about they're obviously distributed to all the schools in the UK, and a lot across the world as well. So that's Joe, and he's a real whiz with anything that involves getting code into very small processors. So you've seen the picture outside the InfoLab, but there are much bigger installations of this. So MK Illumination, the company who's taken this on board and turned it into a product. And this is an installation in Zurich Central Station. And as you can see, it's a vast candelabra of lights, multicoloured lights, not just white ones. And crucially, people who are around the station can go to big touch screens and choose patterns of light that then end up moving back and forth through this big installation. So where did this all begin? Well, it began with a vision. There was a project that Joe and I were involved in, which was all about putting lots of screens all over the campus where we were working at that time in Lancaster. This included sort of fairly obvious ones in the library, big information screens, also outdoor screens, interactive ones where you could go and touch things and see things that are going on. But also we wanted to look wider than the obvious information screens. So one of the things we had was there was a big bus and an underpass in the campus, and it was where the bus stop was. So the buses stopped there and people were waiting. So across the road from that, in this underpass, we had a large projected screen that you could interact with using your phone as well. So there's different sort of ideas. But still, these were all flat screens. Interesting, but we wanted to go one step further. And after one meeting about this idea started to go to head. And I remember talking to Joe and a few others about it after this meeting, and thinking about all those little white lights you see in town centres, sometimes hotels, in the trees. And imagining just if all of those trees, all of those lights in those trees could be treated like a display. If you could have patterns of light moving back and forth through those town centres trees. If you could have something like, perhaps if it's a hotel and somebody's getting married in that hotel, you might have the names of the bride and groom being rotated through the trees, or perhaps somebody's big birthday or something like that. So lots of things we could do if only we could turn all those little lights into a display. But they're of course very, very different from what you think of as a computer display. So we had some goals anyway. What we wanted was lights that we could just put anywhere. Just like when you put your lights on a Christmas tree, you just wrap them round. You don't think about positioning them on a fixed grid. And most lights that you see, most Computer displays are about rectangular grids. We wanted to break away from the rectangular grid. But what we didn't want to be doing was carefully measuring the position of each and every light in order to do it. We also wanted to be scalable. We were interested in tens of thousands of lights, perhaps millions. If you think about a park full of lights, how many of those little tiny LEDs there would be in a park that size? Maybe a whole city connecting them together. So they had to be cheap as well. Each individual light needed to be designed so it could be very cheap, and that drove a few things. There were many iterations. I'm not saying this happened straight away, but Joe, he's a whiz at this. So it was like the day after we had a discussion about this, he had circuit diagrams and very, very quickly actually built some early prototypes. The crucial thing we realised at some point was that what we'd have is behind every single light. So we've got a single pixel, a single light, we would put a little computer chip. And you can see here a single LED with a computer chip behind it. Off a single wire, so more like a networked computer than what you normally think of with wiring is you have switches and each switch connects to a piece of wire that connects to a light. We said get rid of that. Each light is like a networked computer. Which seemed like a bit of overkill, but actually turned out to be the right way to go. And as I said, Joe was brilliant at that, created very quickly some physical prototypes, and we were able to create some simple Christmas trees. But even the one, I'm going to show you a Christmas tree with a prototype with, I think it was 1,000 lights on this Christmas tree. So even then, quite a lot of scale. And to suddenly see the kind of potential there was. Now, this is a lot simpler than the display in Zurich station, but I think you can start to see where we were getting the idea of the potential and what might work. This is a very early version of Firefly. You can see the tree on the left hand side, and you can't see them at the moment, but there's lights in that tree. There's a screen you can see which is in the lab next to the tree, and the area on the right is a close-up of the dark area of the screen. You can probably just see that as well. And what the person at the screen is about to do is draw on the little model of the tree. And the model of the tree, the little dots are the placement of where all the lights are on the real tree. And as the person draws on the model of the tree on their screen, the corresponding lights light up on the tree. So you can sort of basically paint the tree in real time from the screen. And there was versions of this that run on iPads, and in Zurich station there's a big version with touch screens doing something very similar, but to a much larger but differently shaped version, like a large candelabra. So, quick recap. We wanted thousands of lights anywhere, higgledy-piggledy, wherever they could go. We're achieving this by creating a 3D model of the layout of each light. And once you've got that model, then you can use that to control the lights. But how do we build that model in the first place without going to each light individually and measuring its position? And that was our challenge. Now, in fact, for that, we could use technology that is not just recent, but goes back many, many years. And in fact, the technology we used was, you might have done as in school. I certainly did, as I was about perhaps 9 or 10 in primary school. And we went out into the playground one day, and we were in pairs, and we each had a little cut-out triangle of cardboard. And it was a right-angled triangle with 45 degrees ends. And what would happen is one of us would stand and look up the angle of the triangle towards the top of the school wall. And it was, I guess, probably about 20 metres tall, perhaps 25, something like that, the school wall. And then we would walk back and forth until our eyes line was exactly along there, and the partner would be looking at to make sure the bottom edge of the triangle was straight and was horizontal. So we were looking up at 45 degrees to the wall. What we then did was, back in the classroom, we measured the height, we measured how far we were away from the wall. We knew how high we were holding it because it was at eye height. And you added the distance to the wall, because it was a 45-degree triangle, the distance of the wall to the height of the point you were looking at it for, and that gave you the height of the wall. Brilliant, brilliant. Now this goes back, as I said, thousands of years. and certainly hundreds of years in its current form, but the ancient Egyptians knew about doing this kind of thing, and that was used for the pyramids and other things. And certainly, if you've ever done any sort of Euclidean geometry, it goes, Euclid and in the ancient Greeks were certainly thinking very carefully about this. And this is used for things like working out the height of a mountain. If you want to see how high Everest is, you can look two different places. You can look at the angle from the two different places up at it and work out its height. It can also be used on the flat. If a ship is at sea, if you've got two people looking at it, they know they're at two perhaps different observations. They work out the angle to the ship and they can work out how far away it is. And if you can remember to your geometry, if you know two angles and one side, you can work out everything about the triangle. And this is used for all sorts of things, but particularly for map making. And you might have gone, if you ever climbed the top of a high hill or a mountain, you might see a trig point. It's one of these little concrete posts. And here are two trig points. One I've never been to, but looks really nice. It's with this picture with the red dragon on. And that's a mountain top near Brecon. And the other I've put there is Garth Hill, which is just to the northwest of Cardiff. And the reason I put it there is it's just a mountain. There's this little heap on top that pushes it over 1,000 feet. There's been a film made about it. There's a Hugh Grant there. You can see Hugh Grant looking somewhat younger than he is nowadays. It was a few years ago, this film. But it was based on Garth Hill and putting the mound on top to raise its height. And because what's the people in this film does, it's called the Englishman who walked up a hill and came down a mountain. In the early days when they were working out the mapping, on top of these posts you put some instrumentation and then you note a stable point and then you work out the angles to other trig points and you gradually build up a map of the world. And you do that both in terms of where it is left in terms of the flatness, but also you can get the elevation from how the angles up and down. So that's a sort of absolutely standard technique that's been used, I said, for hundreds of years in its modern form and for thousands of years. Of course, what we wanted to do was use this for positioning lights on a tree, and it's exactly the same principle. Now, we used a camera rather than a little sort of device that we were pointing at because we wanted to look at lots of lights at the same time. We didn't want to actually, again, if you've got thousands of lights, you don't want to say, let's position light number 1, light number 2. You want to try and do several at the same time. So what we do is had cameras, and I either had one camera and moved it to multiple positions, or you can think of it as several cameras. Typically it was one rather than several. But think about lots of cameras, or lots of camera positions. And from each camera, if you can see the same light from more than one camera position, and you know where the cameras are, then you can do the same sort of triangulation as you do to find the height of a mountain, the position of a mountain, and you can find the light. Job done. Yeah, great. We want to do this for lots of lights at once, but of course a camera can see lots of lights at once. So if you can identify, and we'll come back to this in a minute, which light is which in that camera frame, you can look at all of the dots of lights here, all of the dots of lights here, choose the one that you're interested in and do your triangulation. Brilliant, brilliant. And from that, you look at your lights, you find the positions of all the lights on the tree, you build a computer model of where all those positions are, and then if you want an area of that model to light up, if you want to brush across that model, you work out from the model which lights are in that area, and then you tell those lights to turn on. And that's how we got the effects you can see in the demonstrations we had, the early demonstrations. So, you know, we're getting there. We now can build our digital model, and we know that once we've got our digital model, everything can go ahead. There is a slight complication. 3D triangulation is not quite as easy as if you want to do triangulation on the flat. So if you know you're in a line and with something, you can do a height. If you're on a perfectly flat plane or perhaps at sea, and you can do two lines on the flat cross at an exact point. Now, with 3D, it's slightly more complicated. If you imagine looking at that light, in principle, if you know exactly where two cameras are and they are absolutely accurate. The line of sight from each should cross exactly at the position of the light. But of course there's lots of things that get in the way of that. The pixels of the camera are not infinitely small, they're of a finite size, and so there's a little bit of uncertainty there. The cameras themselves will almost certainly shake just a slight bit. They won't be absolutely perfectly in position. The lenses on them will have some sort of aberrations. You may not be absolutely positioned, within a few centimetres you might know where the camera is, but even then there'll be some inaccuracies. So in practice, the two lines don't quite meet. And what one does in practice is because they don't quite meet, you look for the closest point, the point where those lines are closest, and use that and then probably take the midpoint of that closest line and use that as an approximation of where the actual light is. Now you can do that if you can do that with a bit of 3D coordinate geometry, if you like. You can do the XYZ line of two lines, equations of two lines, and you can do some minimization to position. And you do that certainly if you have lots of cameras at the same time. But for certainly for some of the early experiments with this, just looked at pairs of cameras at once that were seeing the same one and transformed it into ways to make the maths easier. And now this is something that I do all the time when I do maths, is I make mistakes, I make silly mistakes. And so what I do is I constantly try and transform problems into easier problems. And that transformation might have complexity, but I try to break it down so that in the end I end up with a series of simple problems rather than one horrendously difficult one. So one of the ways of simplifying things, and what you often get this with anything to do with vision and coordinates, you get it with general relativity, if you ever get onto special or general relativity, Einstein and all that. You get it with robotics. What you often do is you transform your coordinate system to make them convenient. So if I've got two cameras and I know the line of sight from them to a single light, what I do is first of all transform it and choose a coordinate system positioned at the first camera. So it's starting with the first camera, put the line of the light in the center of my coordinate system. So it's my XY0 point in that coordinate system. And then I move everything into that coordinate system. So my Z coordinate is my distance out towards the light, and my XY is there. My 0 point is the camera, because I don't know how far the light is at this point. What I then do is, if I know the position of the other camera, I should mention the position I'm doing is not the light, of course, it's where from camera one thinks the light is. And of course the light might not be quite there. We don't know exactly where the light is. All we know is what we can sense through the camera. What we then do is, in that coordinate system, see where the other camera lies, and if we know its position, it's a little bit of, you'll have probably done coordinate transformations in 2D with 2 by 2 matrices. It's just 3 by 3 matrices. It gets a little bit more complicated, but it's more of the same, of things you will have done before and seen at different points while you're at school. And then from that camera position, you look at, in this coordinate system, the angle to where it thinks towards where the light's positioned. And of course it will miss slightly as well by a little bit. So this makes things a bit easier. So now everything's, at least, and one of my lines is not two lines meeting in 3D space. It's now I've got a line out and a line across. And then to make things even simpler for myself, I then rotate this coordinate system round. So imagine twisting the camera around, but I do it digitally. So that the line of sight from the first camera rotates so it's upright, and I make that the new Y coordinate system. Now the reason for doing that is now the point of closest approach is just where that line crosses the x-axis. Hunky-dory, and then the midpoint between that and the origin is our estimate, our best estimate of the position of the point. So if you notice what I'm doing is each of those steps has some complexity to it, but it's a lot easier than working out the equations in full. Sometimes you have to, but if I can get away without doing that, I try. This is almost there. There's one extra little complication. So we've got all our cameras. We can work out where the lights are if we know where the cameras are. Sometimes we can really carefully measure them. Sometimes we might know a bit more approximately. If we're not absolutely sure of the camera positions, we might need to do some extra work to work out where the cameras are. And in principle, if there's enough lights, you can work out where each camera is relative to that bunch of lights, or each camera relative to each other. And it's a technique that's used in various purposes. And it's an example that's called an inverse mapping problem. If you know the position of the cameras, then you can work out where the lights are and everything's easy. But of course you don't know, if you don't know where the cameras are, you have to do extra work to work out where they are. So if you know them, you've got an easy solution. But you actually have to sort of turn your maths backwards. This is more complicated. I won't describe it in detail how you achieve this. And sometimes you have to drop to sort of fairly crude numeric techniques to get there. Sometimes you can be a little bit cleverer. But I'll leave that for another day. So let's recap. We want thousands of lights. We want them anywhere. We've used triangulation to find the position of each light and built a 3D model using that. And then from the 3D model of where the lights are, we can turn them on and it becomes a display. However, there was this little question we had about the lights themselves. When you've got a camera and you can see all those little white dots, which is which? Now, in this picture, the tree's got different coloured lights. In those early ones, they were just white or not white. But even if they're coloured, there's a lot of blue lights there, a lot of pink lights there, a lot of green lights there. How do you know which blue light is the same blue light? If you were looking at a mountainscape and trying to work out the height of Everest, you'd sort of be able to work out from the shape of it, oh, that peak there looks like Everest, and know which is which. But if you've got lots of lights that are the same, how can we do this? In fact, the way we work out which is which is rather like fairy lights, because we make them twinkle. So basically during a calibration stage early on, we just make them twinkle. This is not part of the display, it's part of something you do up front to build this model. So while you've got all those cameras doing the 3D triangulation, the lights are twinkling, and they're not twinkling randomly. Each light twinkles its own code. It flashes its code. So you can see it's light flashing here, and when it's on, you treat it as a 1. When it's off, you treat it as 0, just like sending a message over a computer network or through Wi-Fi. There's some extra little complexities. You tend to have to do a little pattern at the start so you know when it's starting. But on the whole, you're just flashing its light. All well and good. However, of course, the main example we thought of, the starting example, was lights in a tree. And of course, trees have leaves. So if the leaf happens to get in the way of the light, and especially if it blows back and forth a bit, perhaps one of those flashes gets missed and you end up with a totally wrong code. There's other things that might cause this as well. It might just be that a bird flies past. Or if two lights happen to be nearly in line with one another, they would just appear at the same point on the camera, and then their codes will just get mixed up with each other. And this is particularly crucial during calibration, because this is the thing you're doing to build the model. If the model is wrong and you've got the position of one of those lights wrong, when you want to light up an area and you think the light's in there and you turn it on, in fact, you'll get this single little blob of light will appear in completely the wrong place. So it's really important during calibration to get these things right. So what do we do about it? Well, happily, there's a whole load of techniques of having coding numbers like this in ways that you can either detect if something's gone wrong, and if you know it's wrong, you can ignore that and perhaps do another calibration run or use other camera positions, or even sometimes correct some of the things, put some things right that were wrong. If you get the leaf flaps over, you can sometimes fill in the gaps. So let's see how this works. You've probably come across one of the sort of simplest forms of error detection, which is parity. So when and there are more sophisticated versions, but the simplest version works for binary codes. And what you do is you add an extra bit to the end of the code to make an even number of ones. So if the code was 0010110, which is the one we had a moment ago, which coded to 42, then there's an odd number of ones in the original code, so we add an extra one on. So we turn our 8-bit code into a 9-bit code, and we've got an even number of ones now in that code. If it had started off with an even number of ones, 1110, 1110, then we add a 0 at the end. And then what you can do is you can you read your 9-bit code from the camera position, flashing out. You can look at that, you can see how many ones there are in, and if the number of ones is odd, you know there's been a mistake. And this can detect single bit errors. So if there's a single bit goes wrong, if 2 bits goes wrong, then all bets are off. But certainly it corrects. If just 1 bit goes wrong, you can know something's gone wrong and just ignore that and perhaps look for the next signal. So far so good. That gives you 1-bit corrections on 8-bit codes and binary codes. But in fact, you'll have seen other kinds of error correcting code. You know, I published a book recently. I've published various books in my time. Very often on the back of a book, there's a little barcode. And the barcode crucially codes an ISBN. An ISBN is a number that uniquely identifies the book, not the particular copy of the book, but which kind of book it is. And it's a 13-digit number. Older books, you might just find a 10-digit number, and the last digit sometimes is an X, and that's done slightly differently. But most books now will have a 13-digit ISBN number. And it consists of 12 digits that actually are the code of the book. So here, 978168173 and an extra check digit at the end. And in this case, the check digit is 0. The way the check digit is calculated is using mod 10 arithmetic. So you might have done this modulus arithmetic or remainder arithmetic, where you add up numbers and then you look at the remainder when you take it off. So mod 10 arithmetic is just basically adding up numbers and ignoring everything apart from the last digit. So you drop all the digits before. And what you do to get your check digit here, you take the first number, 9 here, add 3 times the second digit, add 1 times the third digit, 3 times the fourth digit, and go on until you get to the end. Then take the whole lot mod 10. So you basically throw away everything but the last digit and then subtract that from 10. And then again, throw away everything but the last digit. So for most, you end up with a number that's 0 to 9, that's 1 to 9, but 0 from 10 is 10. So again, you just drop the last one, so 0 ends up as 0. And then you put that as the check digit at the end. If you then are scanning the number on the book with a barcode reader and the scanner reads that number, if there's a mistake in the number, the check digit won't come out right. So it'll recalculate the check digit, and if it doesn't come out right, it'll know something's gone wrong. This particular kind of check digit is slightly more resilient than the binary one we talked about a moment ago with parity. It's resilient for single-digit errors, so a bit like single-bit errors. So if any of those digits, if you're writing down the digits and you put a 6 instead of the 8, you'll get a different checksum and therefore it'll detect it. But also if you swap 2 digits, the reason for the 1s and 3s alternating means if 2 digits swap, you also notice. So for instance, at the beginning, if you were to look at 798, you would end up with a different check digit. And so you'll know that and certainly for writing ISBNs down, that's a very common mistake to make, just to put 2 digits the wrong way around, it'll detect that. More complex mistakes it won't detect again, but it'll detect swaps and it will detect single-digit errors. I would particularly like to poke out though this 3 and the 10 here, right? The crucial thing about the 3 and the 10 for this to work as a resilient code is that they are co-prime. So I'm not sure if you've come across the phrase co-prime. You know about prime numbers. So a prime number is a number that's only divisible by itself or 1. 2 numbers are co-prime if their only thing that divides them both is 1. So 3 and 10 are co-prime because the least common denominator, the only thing that divides them is 1. But 4 and 6 are not co-prime because 2 divides them both. So now why is it important that 3 and 10 are co-prime? Imagine if instead of 3 we'd chosen 5. So we said 1 times the first digit plus 5 times the second digit plus 1 times the third digit. The second digit, now in this case it's a 7, right? So 5 times that would be 35. We're doing everything mod 10, you drop things down, it would become a 5. And in fact, every odd digit would end up coding to a 5. So if the 7 were actually written down as a 3, they would end up with the same check digit. Because 3 and 10 are co-prime, 3 effectively shuffles the numbers in the code. So imagine, if you just think about your 3 times table and just look at the last digit. 0 goes to 0, 1 goes to 3, 2 goes to 6, 3 goes to 9, all the way through. And if you look at them, they're all different from each other. It's shuffled them up, not in a sort of randomish way. And this pattern of multiplying by a number and then taking the remainder with some co-prime number is something you see in lots of cryptographic things. It's used when you want to do digital signatures. It's used for encodings. And we'll see another example of it a little bit later on. So how do you build codes that are stronger codes, these codes, and ideally we'd like some error correcting codes as well. So one way to sort of think about this is to think about your code geometrically. So if you I'm going to go again for binary numbers here. And what I'm going to do is treat my binary number as if it was the x, y and z coordinates of a cube. So I've got that sort of back right, back left one I've got as my origin, 0, 0. I've got 1 is my up axis. The first number is encoding the up axis. The second number is the left to right axis, and the third number is the one that's coming in and out to us. And you can see I've labelled this cube as if these were coordinate axes for each one. If you have an n-bit binary code, this is the 3-bit code. If you have an n-bit binary code, you end up with an n-dimensional hypercube. So I'm going to think about codes as n-dimensional hypercubes. Wow. Now, I can't really think that well in many dimensions. 4 I can sometimes just about manage, but, you might need a 13-dimensional hypercube here. So I can do the maths of hypercubes. I can't always visualize them, but certainly for 3 we can visualize. And I'll use this to sort of give an explanation of what you do. Now, if you represent numbers of hypercube like that, you can ask, what happens if you have a single bit error? Well, on this number here, we've got 0, 0, 0, 0, 1. If there's a single bit error in the last digit, then you move across, you end up with 0, 0, 0, which is a traversal. It effectively takes you along one of the edges of the hypercube. If there was a mistake in the second digit, then that takes you along another edge of the hypercube. If there's a mistake in the first digit, it takes you along another edge of the hypercube. And in general, single digit errors or single bit errors correspond to the edges from the vertex you're at in this hypercube. So you can sort of translate from errors in digits to geometry of a hypercube. If we want error correcting code, things have to be far enough away that that little area of errorness is distant from the area of errorness of other things. So we've got the error balls, in a sense, in this multi-dimensional space to be distant from one another. So if you think about this, if you think about the globe, it's a bit like trying to find points that are farish away from one another so they don't get mixed up very easily, even if you're not quite certain where they are. I said it's, you can conceptualize it. The maths of it gets a little hard. I won't go to the great detail on this, but just to give you just the general idea. For the 3-dimensional case, let's start off with the 0, 0, 0. Imagine we want that to code for red. We'll code colours out of this. So we're going to try and code as many colours we can on this hypercube. So we'll use 0, 0, 0 to code red. The single bit errors from those, the things that could be that if you're 1 bit wrong from that, are the ones at the edges of the vertices at the edges connected to that one. And in general, if we want something not to be mistaken from that, we need it to be at least 3 edges apart, because each one can have a 1-edge error, and if they both got a 1-edge error and end up in the same place, then you don't know which is which. So what you do is you look for things that are at least 3 edges apart, and here's 1, 1, 1, 1, and if you look at the things that have got 1-bit errors from that, these two sort of potential things that errors are actually distinct from one another. So these are safe codes. They're codes that if we use those to code for red and blue, if we only have 1-bit errors, we're not going to mix them up. So from our 3 cube, we managed to code 2 values. We're not doing that well, but we can correct 1-bit errors on these. So note that was a 3-bit code for a 1-bit number. So we had to actually add quite a lot of extra information in order to create an error correcting code. You notice 1 bit, the parity bit, was sufficient for an error detecting code, but to correct it, to be able to say, if something's wrong, we'll be able to work out where it came from. We need to add correspondingly more information. Happily, it's not always 3 times as much. So in fact, a 13-bit code is sufficient for 8-bit numbers. But in general, it's the same pattern, just adding codes to the end. So let's recap again. We've got 1,000 lights, we know that. We're going to flash the ID as an error correcting code of each light. By doing that, we can then know which light is which. We can use triangulation with the cameras to build a 3D model. Yay. I think we are starting to get there. We're getting to it. So we've got those IDs. But how do the lights get their IDs? How do we get an ID onto each light so that it's distinct? And names matter in so many things, but getting a unique ID of something is really important. Now, for some purposes, you can actually factory assign them. So you can buy computer chips and voice-based chips with a unique ID burnt into them at the factory. A bit like printing the ISBN, but rather than just saying that this is a particular kind of book, if you had an ISBN that said, and it's this very, very particular copy of it. So, and that's used for things like network chips and computers. They have a very specific ID burnt into them so that it's unique from and guaranteed to be unique from day one. Unfortunately, that costs more. It tends to put up the cost by doing that because it's an extra process. You're not just rolling out more and more of the same. You actually have to make each one different. And that adds to cost, and cost causes problems if you want to have large scale. So you want to have things that are each individually very cheap and are produced in quantity. Then obviously you want to make each one as cheap as possible. So that's the reason why we wanted to avoid factory IDs if we could possibly do it. Another thing you could imagine doing is if you've got a string of lights, if you're in a group and you're playing a game and you need to have numbers each, you might go round and stand in a circle, and the person that start off and says 1, the next person says 2, the next person says 3, all round until you've all got a number. That works if you can see each other and you know who's next. You can have ways of connecting chips onto wires that work like that. So the wire connects into one side of the light. You can imagine that. One wire connects into one side of the light, another wire connects into the next that goes onto the next light. The powers pass between, but it sort of does some signaling. So it passes on the messages in a sort of round robin style. The problem with that is one is introduced delays, but perhaps more crucially, if you're relying on it passing on messages, if any light fails, the whole string fails. So we ideally don't want that because things can go wrong. So most computer things are not designed like that for that reason. I mean, it used to be, it was more common to see that, but most networks nowadays do not work that way. In fact, our lights, and you can sort of see that there's just a single wire and they're plugging into that wire. And that's a very common way to arrange networks. But also if you went for a wireless version of these, of course, even then there's no way you can do a round robin because everything's just getting it wirelessly. So there's good reasons not to go for the other ones. But so what do we do? If they don't know their number, they're all sitting there, how do we get an ID? What we do is we ask the lights to randomly choose an ID for themselves. Right? I don't know whether you like your randomness or not, but that's the way we do it. We get them to ask a random ID, or at least the way we thought about doing it. Now, in fact, there are lots of things that are used in practical day-to-day life where IDs are done like this. A lot of some of the big cloud computing platforms, the sort of things that Google use. When you have data created in lots of places, the way to give it each of those an ID is often to create a quite long random ID. And if those IDs are long enough, then the chances of two ending up the same, even though random, is low enough that you might not care. So how long is long enough? How big does ID have to be before you think that the likelihood that two people or two chips will end up choosing the same one is a problem? We wanted to use ideally 8-bit IDs. The reasons for this is good computery stuff, all sorts of things like that. If you've got 8 bits, we wanted to keep 0 and 255 special. And this is often done in networking for sending a message to everything rather than to a specific location and things like that. That gives you 254 addresses left. Now, we were thinking of strings as typically with perhaps 80 lights on a string. So 80 lights on a string is about a third of the lights on the string. So we're only using about a third of all the possible IDs that you could have for those 254 addresses. That seems quite reasonable, doesn't it? I don't know if you think about it. A third of them, you can imagine throwing them in allocated. You're not going to get too many bumping into each other, or are you? This brings us to what's called the birthday surprise problem. So obviously, imagine it's your birthday and 30 people come. Perhaps you've gone you're in a school class and you've gone to school class, or you're working with people. You're 30 people. What's the likelihood that somebody else has got a birthday the same time as you, the same day as you? Well, there's about 365 days in a year, give or take a leap year. 30 of you, that's about 1 in 12. So it's not that likely. So if I was to sort of, if somebody was to sort of say, I'll give you, if somebody's got the same birthday as you, you have to give me an extra slice of birthday cake. But if they don't, then you get the extra slice. You might well say, oh yes, I will believe that everybody's different from me, and you're probably on a winner there. Now imagine you're with 30 people and somebody at the front of the room, the tutor perhaps like myself giving this lecture, says, I'll bet 2 of you have got the same birthday. Well, you think to yourself, nah, 365 days, 30 of us, what's the likelihood of that? And it feels unlikely. It feels like 1 in 12-ish, but it isn't. It's 1 in 12-ish if you look at any particular person and ask if anybody the same, but of course there's lots of people. And it's the pairs that start to add up, and each pair of people has to be different from one another. So let's look at how those pairs start to stack up. So if you've got one person on their own, there's no connection, there's no paired person. If you have 2 people, there's one possible pair. There's that person, that person. If they've got birthdays, I have to be different from that other person. Now imagine there's 3 people. There's now 3 connections. So my birthday has to be different from the first person's birthday and from the second person's birthday, and the first person and the second person need different birthdays. If there's 4 people, there's 6 possible pairs. If there's 5 people, there's 10 possible pairs. And if there's 6 people, there's 15 possible pairs. And in general, for n people, if you've got n people, there's n times n minus 1 divided by 2 pairs. You might have come across this as the combinatoric. It's a number of ways of choosing 2 things out of n. Crucially though, this goes increasing with the square of n. It's a squarey sort of thing. It's half the square and a little bit less, but it's going up squarish-ish. It's not going up linearly. It's not twice as many, 3 times as many. It's squaring. So as this number increases, so if you get up to, say, 100 people, you'd then be talking about 50 times 99. So nearly just short of 50,000. Divide by 2, just short of 25,000 different pairs. So you can see how quickly these numbers go up. What about our IDs? Even with 20 lights, there's 190 different pairs that all have to be different. And we've got 254 codes. Now, it's not quite, that looks two-thirds it. Actually, there's a little bit of overcounting goes on here. So it's not quite that, but it gives you a sense that there's a lot of things that have to be different. And in fact, if you do the sums precisely, you're more likely than not to have a clash. In the birthday case, if there's more than about 25 of you in that group, you start to be more than even chances that 2 of you will have the same birthday. If you've got 80 lights, actually there's more than 3,000 different pairings that have to be different. Again, that doesn't mean the probability is bigger than one that you'll actually have a pairing, because I said there's a bit of double counting, but it does mean you're pretty certain to have a pair, to have some clashes, and typically probably about 50 of them. So probably only about 30 of your lights will end up with unique IDs when you first have a go at it. And in general, you can do your sums, and if you've got M lights and you've got N addresses, and M and N are biggish numbers, it's M times E to the minus M divided by N. So E is that magic number that you get up if you're doing, it appears if you're doing things like differential equations. If you've been looking at COVID and the modelling of how diseases go, you get exponentials there. So anywhere you get one of these exponential growths, you get these E's appearing. So we've got some sort of E-ness appearing here. You know how many are uniquely allocated, and it's there's M, 1 minus that are the ones that have got clashes. So basically, you know, unless we have some really big address spaces, which then cause all sorts of trouble with other things in terms of practical stuff, it's these 80 lights are going to start having clashes. We're not going to avoid that. We can work out exactly how many we'd expect to have. We can also work out how many times you might have to do stuff. So what's the solution? We randomly allocate the IDs, but we detect whether there's clashes, and I won't describe how we do that, but that's using a bit of electronics. We then say to the lights that have got unique IDs, keep the IDs you've got. To the ones that have clashes, you know which ones are free, which IDs are free, and then they reallocate themselves amongst the ones that are free. And basically, there's the density reduces. You have more free space usually at each one of these goes, and you keep repeating that until either they're all unique or you just say, oh, give up. The ones that have kept clashing for so long, we'll just say are dead lights, and we were just as if they were dead ones in the factory, and we just will ignore them. So that's a good practical solution. It works. Now, I was doing the maths to work out how many runs you'd need to get this to work. Joe was happily going away coding this, and actually when I say coding, not just coding it, but actually running it on lights. And I'd like to say I got there first, but actually I think we were about evens there, and he might have got in front of me. So, you know, practical electronics 1, and I'm afraid maths 0 in this case. However, the crucial thing that I could say is it's not just about these experiments. We could actually be able to talk about, to be able to know in general, if we had, say, bigger runs of lights, what would happen there. So there was some advantage to the maths, but I said Joe did sneak in there first, and in practice, 2 or 3 runs of this tends to get everything sorted. There is a sort of like a meta issue here, which is again and again and again in so many areas I've found this power of randomness is incredible. So, you know, as a mathematician, as a computing person, one thinks about doing things that are deterministic, that are fixed, but actually often random things work better. And this is true. There's lots of biological examples of this. In telecoms, there was a few early disaster stories where a telephone exchange went wrong. All the telephone calls rerouted themselves to the next best exchange. Of course, it then got overloaded, so it went down. And then the next one went down. At one point, I think half of the US telephone network collapsed because of an error like this. Nowadays, what they do is they use a little bit of randomness. They don't necessarily go to absolutely the best place, but one that's nearly the best, but a bit randomly chosen. And by using the randomness, you end up with something more robust. And so it's again and again this story. Randomness can be surprisingly powerful. So let's recap again. We choose random IDs, but detect if there's clashes and reallocate them until they're unique. We can then flash the ID with an error correcting code, use triangulation, build our 3D model. Whew, almost there. One slight gap. How do we get those random numbers, right? Now, each of those lights has a computer behind it, and we know computers do things step by step in sequence. really repeatable, reliable because they're repeatable, very, dependable things, but not random, very sequential, very deterministic. So how do we get a deterministic computer to produce random numbers? Now, you might have actually used random numbers if you've done any coding to get random numbers out. So it's also clearly there are things being generated. However, they are not really random, and we'll explain this in a moment. Now, if you want a really, really, really random number, what you might do is, like for the lottery, they use ping pong balls. Putting ping pong balls into each of our lights was not an option. What you do with computers, you have something that's called a pseudo-random number. It's not actually random, but it's random enough. And one way to think about this with sort of maths hat on is to think of the digits of pi. So pi, we know it goes on forever, the digits it's got. And there's, people have calculated the millionth, the 3 millionth digits of pi. And there's books you can get all the digits of pi on. Crucially though, if you look at those digits, they are not random. They are a deterministic thing. They are a particular amount. They are the ratio. They're the digits of the ratio of the circumference to the diameter of a circle. They're a very precise kind of thing. However, for all practical purposes, they appear random. Every sequence of numbers recurs again and again and again, and you can't predict how often and where it's going to come. You can calculate them, but you can't. They appear to most purposes as if they were random. And if you wanted to just do random numbers between 0 and 9, if you got one of these books of pi digits, opened it halfway through and just started reading them, it would work pretty well as a sequence. And computers use a very similar things. They don't use digits of pi because it gets harder and harder to calculate the extra digits, but they use a sequential method that generates things that are, for practical purposes, appear random. And many of them are based on taking a value, multiplying it by a large prime, and taking that modulus another large prime. From things I've said before, you might have already worked this out, actually they don't actually have to be prime so long as they're coprime. And the idea is if you multiply something by a number and then take it modulus another number, if those two are coprime, then effectively it acts a bit like a shuffle, and it shuffles all the numbers around. And if these are big numbers, big prime or coprime numbers, then it shuffles it around so much it appears to be a random sequence you get at the end. Typically what you do is you do this process, but very often you don't necessarily take the whole number as your random number. You pull out the middle so many digits and you use those and you iterate that way. But many are based on this kind of principle, but also lots of cryptographic techniques use this kind of technique. And as I said, it's just like your ISBN. Your ISBN, it was 3 and 10. Here, often the digits are very, very long, but it's exactly the same principle as used for creating the check digit on the ISBN. But there's a little slight problem here, again, a practical problem. The computers are all identical. Each of those lights is identical. They've come off the factory in vast quantities. So this is our early prototype lights, our second prototype. The first was handmade. The first time we had something produced in a factory. And they're all the same. They're all the same. So why is that a problem? Well, you might have heard of, and if not, you can look it up, a film about Spartacus. And Spartacus was this person who led a slave revolt in Rome. And there was a film made about Spartacus. And at the end of the film, the Romans have won in the end, but they don't win the moral victory. Of course, Spartacus has. But Spartacus and all the slaves are the ones who've survived the fighting are all lined up. And the the Roman governor says, Spartacus, please stand up, and if Spartacus stands up, he'll get really, really nasty killed, and the rest will get killed in a slightly less nasty way. So Spartacus is both about to stand up in order to save the rest of the people from having really, really nasty things happening to them. But in fact, before he's able to say, I'm Spartacus, somebody else says, I'm Spartacus. And then somebody else says, I'm Spartacus. And eventually the whole slave army, or the rebelling slave army, say, I am Spartacus. And course, he never knows who which, so he just kills them all. But happily, nobody's getting killed here. If you ask your lights, what's your ID? Of course, the first one says, well, let's say I'm 42. The second one says I'm 42 as well. And the third one, and the fourth and fifth, and they all will give the same number. If they're all counting, although this sequence is pseudo-random, if you all ask them, so what happens? You turn them on, they start calculating their random number, and then you say, what's your random number? If you ask them all at the same moment, they've done the same number of steps in this process. It's a bit like the digits of pi. If they were calculating the digits of pi, wow, it's hard to say. And you've waited 100 clicks and they've got as far as calculating the 100th digit. They're all calculating the 100th digit. You ask them what it is and they'll give you an answer. I mean, to be honest, at this point, I said we almost gave up and we almost said, okay, we're going to have to bite the bullet and we're going to have chips that have got IDs built into them at the factory and it will cost more, but we're going to have to go for that. And we didn't want to. And then, I don't know why, I just had a brain thought and I said to Joe, I said, how accurate are these chips? And Joe's eyes lit up like light bulbs, like little shiny LEDs. I didn't know, it was just a question. And in fact, the clock on the chip, there's a built-in clock, it's a little oscillator, is accurate enough for most purposes, but it's perhaps got 1 in 1,000 bits error to it. If you want something really accurate, you can stick on an extra oscillator next to the chip, and if you perhaps wanted to have make a digital clock, for instance, you want something more accurate. But even digital clocks drift slightly relative to one another. But the built-in oscillators in these are not that accurate. And in fact, so these chips are actually all timing themselves at slightly different rates. Some of them are running very slightly faster, some of them are running very slightly slower. So that actually means that if you let them all run for a little while and let them calculate, start calculating your random numbers and they're going through their sequence, and then you come and you say, what's your ID now? They've all actually progressed slightly different distances through the same sequence, so they end up with slightly different numbers. And in fact, we were able to use chips with no IDs because of this. And this is another one of those wonderful lessons that sometimes when things are too perfect, and you find this again in so many examples, certainly when I've been applying mathematics to things, where things are absolutely perfect, sometimes they don't work. And it's sometimes the cracks, the little gaps between the perfection, where the most amazing and useful, in this case, and sometimes beautiful things happen.